Hello everyone, I'm going to be solving an area moments of inertia problem today. And let's dive in and take a look what one of those looks like. So generally speaking, there are two types. There are the types that involve composite shapes, and that's the one that I'm going to be solving for y'all today. This type is, I'd say, easier because there are no integrals involved. It's just, well, assuming you have a table of some sort that provides all the essentials. So I'm trying to decide how I want to define these shapes. So it looks to me like we have shape 1, shape 2, and shape 3. So what's given in this problem? So we're given this is 50 and 50, both in millimeters. We're given there's this thickness here that's also 50, and then 250 is that link's right there. So what do we do here? Well, the first part A, says determine the location of y bar of the centroid of the channel's cross-sectional area. So what is y bar? Well, y bar is going to be some distance from the x-axis, which we'll define to be at the ground here, right? Some distance up to the center of mass. Now, how do we find exactly where that's going to be? Well, we know, of course, that y bar is going to be equal to, for composite shapes, it is the sum of the area of that shape times y, the distance from the x-axis of that shape, times the area total, or the total area of the entire body. So we'll have to find ai and y sub I for each of the three shapes, like such. So the area of shape 1 is equal to the area of shape 2, which is 200 times 50. So 200 times 50 is at 10,000. And we know that 2 is going to be the same. And then 3, I didn't write that distance, did I? That's actually going to be 350, that bottom distance there. 350. So it's 350 times 50, which is 17,500, like that. So then the distance from the y-axis for the first shape is going to be the same as for the second shape. And it's the distance of the centroid of just that one shape, right? The middle of that one shape. So for the first shape, we know that the shape is a height of 200, right? So whoops. So given that it has a height of 200, we know half of that is 100, plus that 50 at the bottom is 150. Likewise for shape 2, it is also 150. And for shape 3, it looks like the width there is 50. So here it's actually only going to be 25. So next, we need to multiply each of those values. So the first one is going to be 15, and then tack on the 5, 1, 2, 3, 4, 5 zeros. The next one's going to be the same. And then the bottom one, I'll have to type into my calculator, and it looks like that's going to be 4, 7, I'm dyslexic, 4, 3, 7, 5, 0, 0, like such. And then we're going to take the sum of those. So that plus 1, 5, 0, 0, 0, 0, 0 plus 1, 5, 0, 0, 0, 0, 0. And it appears that that's going to equal 3, 4, 7, 3, 4. Do I have issues? I do have issues. No, I don't. Yes, I do. Whether I made a mistake or not, I have issues. So there we go. And we get that. And then it's going to be this number over AT. So AT is actually just going to be all these areas summed up, which looks like it's going to be 37,500, like that. Let's type that in the calculator and see what we get. And we get, for y bar, let's write it over here, let's say, y bar is equal to 91.6767 meters. All right, so that was the first part of the problem, to find y bar. Although they're just sort of guiding us through the problem, that's just a necessary evil in order to find the moment of inertia about the x-axis. So then how do we go about doing that? Well, there is a nifty formula that is I of a how do you spell that? Parallel, like that. Parallel axis is equal to the I centroid, or the moment of inertia centroid, plus distance squared A. And what is meant by that distance? Well, let's see. So for this problem, I total is going to equal I1 plus I2 plus I3. So now we need to know what I1 equals, I2 equals, and I3 equals. So I1 is equal to I centroid plus d squared A. So what is I centroid for a rectangle? Well, I'm going to refer to a chart that I have, but normally you'd have to do some, not too hard, but a little annoying to do several times, calculus, right? So our ultimate goal is to find I of t, which also happens to be about the x-axis. So I'm going to use my equation for Ix, which is bh cubed over 30. What is wrong with me? I was looking at the triangle one. bh cubed. There we go. Plus the d squared A. So I'm going to drag these down, and we'll do those off screen in a minute to give myself a little bit more real estate. So 1 over 12 and times b, where b is the base of the rectangle, which is 50, times the height of the rectangle, which is 200 cubed, plus d. Now that d is referring to the distance from the center of the rectangle I'm evaluating that I said earlier was half of 250, which is, or half of 200 rather, based off how I defined it, half of 200, which is 100 plus 50, so it's 150. So this is 150, and y bar, right, we found in the last part of the problem to be 91.67. So all that d is in that equation is the difference between those two numbers. So 150 minus 91.67. And that is going to equal 50.83833, if I'm not mistaken, which it looks like I am. 50. I'm gonna have to type this in a calculator. My brain's on 2%. 58.3.33 squared and times the area of that piece, which we found up here is that, which is 10,000. Maybe I didn't need the extra room after all. Maybe it's going to fit on one line for me, just nice and tidy. So that's 200 cubed times 50 divided by 12 plus 58.33 squared times 10,000. That is a rather large number. But I'm just now realizing that that's because I didn't convert from millimeters. So my previous answer should have been in millimeters, so this answer should have also been. But as long as I'm consistently wrong, then I suppose I'm okay. 6.73 times 10 to the 7. And because it looks like I'm going to be able to fit all this on one line, and I'm going to say that I2 is the same as I1 because it has the same features and it's the same distance from the axis that we are evaluating from, which is the x-axis. So 6.73 times 10 to the 7. And then this one's different, of course, but it's still the 1/2 base times height cubed plus d. So the d in this case is 25, so it's 91.67 minus 25, which is 66.67, and that number is squared. And then we're going to multiply that by the area, which we also calculated in the previous section to be, or the previous part rather, to be 17.5. Just like that. And then I'll plug all that into a calculator and we'll see what we come up with. Type in numbers. And we get this large number. I'll write it in scientific notation. And then if we add those numbers up with the previous large numbers, it looks like we get, the correct answer. So I of x, the area moment of inertia is 2.16 times 10 And it looks like it's to the 8 now. And now I didn't change it to millimeters, so it's actually going to be meters. And the units on these guys are to the 4th power. So there you have it. Not too bad. I didn't change units, but obviously doesn't change the problem any. And that's all there is to it. Let me put it all in frame for you. I tried. Doesn't quite want to stay in frame. But there you have it. There's the problem. Pretty straightforward. Hadn't they told you to find y bar, you still would have had to have found y bar. It's pretty straightforward. The formulas aren't too difficult to memorize, luckily. And that is that. I hope y'all enjoyed, and I will see y'all for the next one. If I survive to it, that is.